A real-world graph is not just a picture. It is a compressed argument. It claims something about what was measured, who was measured, and how values compare or change. Interpreting a graph correctly means unpacking that argument before you react to the shape of the lines or bars. Start with the scaffolding. Always read everything around the data before you read the data itself. Look at the title. Is it neutral, or is it pushing a conclusion? Unemployment rate from 2010 to 2024 describes. Unemployment is exploding persuades. Then check the source. A government agency, a peer-reviewed study, and a company's marketing team all have different incentives. That context matters. Next, read the axes slowly. Ask yourself what is on the horizontal axis, what is on the vertical axis, and in what units. Percent is not the same as counts. Dollars are not the same as inflation-adjusted dollars. Most mistakes come from skipping this step. Closely related is the denominator. If a graph says 10,000 cases, your next question should be, out of how many people? Counts without population size are usually meaningless. Once you know what is being measured, identify the kind of data. Some variables are categories, like country or brand. Some are ordered ratings, like 1 to 5 stars. Some are truly quantitative, like income or temperature. This matters because not all comparisons are valid. You can average incomes, but averaging categories makes no sense. You can compare proportions across groups, but you should be careful about comparing raw totals. Now look at the scale, because scale choices can change the story without changing the data. Check whether the vertical axis starts at 0. In bar charts, a non-zero baseline can make small differences look dramatic. Sometimes a truncated axis is justified, but it must be clearly labeled. Also check whether the scale is linear or logarithmic. On a linear scale, equal vertical steps mean equal absolute changes. On a log scale, equal steps mean equal percentage changes. A straight line on a log scale means steady growth rates, not steady increases. Different graph types answer different questions, so read them differently. A line graph usually shows change over time. Look for the overall trend, the speed of change, and any sudden breaks that might signal a policy change or a new measurement method. Remember that cumulative lines almost always go up, even if the underlying rate is falling. Bar charts compare categories. Compare bar lengths only if the baseline and scale are honest. Ask what is hidden inside each bar. Large averages can mask very different distributions. Histograms show distributions, not categories. Read them by describing the center, the spread, the shape, and any outliers. A common mistake is to treat histograms like bar charts and forget that the bars represent ranges of values. Scatter plots show relationships between two quantitative variables. A correct reading mentions direction, form, and strength. A tight upward cloud suggests a strong positive association. A loose cloud suggests a weak one. And a scatter plot alone never proves causation. Even a clear graph can still be statistically misleading. Ask about sample size. How many observations are behind this picture, and are they representative? Ask about uncertainty. If the graph shows averages, where are the error bars or confidence intervals? Differences smaller than the noise should not be overinterpreted. Be especially careful with relative versus absolute change. A 10% increase sounds large, but if the risk went from 1 in 10,000 to 2 in 10,000, the absolute change is tiny. Responsible interpretation keeps the denominator visible. Also ask what else could explain the pattern. Group comparisons often hide confounding variables, like age, income, or prior conditions. Aggregated trends can even reverse when you break the data into meaningful subgroups. Finally, translate the graph into words. If you truly understand it, you can say something like, from year A to year B, the value increased from about this to about that in these units. Group X is roughly this much higher than Group Y, with this level of uncertainty, and because this is observational data, causation is not established. If you cannot say those sentences, you are reacting to design, not reading data. The core skill is not advanced math, it is disciplined questioning. Slow down, read the scaffolding, check the scale and denominator, match the graph to the question, and demand context and uncertainty. Do that consistently, and real-world graphs become evidence you can evaluate, not pictures you have to trust.